All right, this is section 4.1, video number 2. In video number 1, we talked about different ways of using rectangles to approximate areas beneath a curve and between the x-axis, given the fact that we don't necessarily know the shape or the geometric shape of all the curves as far as being able to find exact areas. So we used 3 different rectangular methods. In this one, we're going to use trapezoids instead of rectangles. So we're going to use the same function that we did before, and I'm just going to kind of try to draw a loose sketch of that. So it looked something like that, and then this was 4. Okay, so we had our partitions as 3, 2, 1, and 0. So the idea was, if we use rectangles, we would either use the upper right-hand corner or the upper left-hand corner or the midpoint of the top of the rectangle to give us the height of the rectangle. The bases we could figure out by figuring out the difference between the x values. It's going to be a similar idea, except this time, instead of using rectangles, once again, we're going to use trapezoids. So what I'm going to do is I'm going to put a point at each one of our partitions on the curve. And what we're going to do is we're actually going to create trapezoids between those partitions. So what I'm going to do is I'm going to draw a vertical line to kind of separate all these. And what those vertical lines are becoming are basically the bases of the trapezoids. The height of the trapezoids is the difference in the x values. And then we've got this piece right here, which creates the other side of the trapezoid. And then on this one, you've got this piece, which creates the other side of the trapezoid. As you can see by my drawing, that's pretty close to the actual shape of the curve. This one's even closer, and that one's probably even closer. The one I really wanted to highlight with you guys is between 3 and 4, because you can clearly see the difference between the curve and the trapezoid. Looks like we've got somewhat of an over approximation, and all of these will technically be just slightly over approximated. But the general idea is it's still going to be a relatively close approximation. Now we just have to remember the formula for trapezoids, which was 1/2, not negative 1/2, 1/2 the sum of the bases times the height. Well, in this case, we've got 1/2 is 1/2 in every problem. All of the heights are going to be the same. All the heights are the distances from here to here, from here to here, from here to here. Those are all your heights. They're all 1. So I can kind of pull the 1 out to the front. Now the nice thing is I can add up all of these bases in such a way that I'm going to show you the long way, and then I'll kind of, hopefully you'll get the idea of the shortcut. So let's go ahead and label all of our bases. First of all, the first base is 0. There's no height to that whatsoever. The second one was 1. The next one was 4, then 9, then 16. And that just came from plugging those x values into the original y equals x squared equation. So if I'm going to add these up, the first trapezoid is going to be the sum of the two bases, which is going to be 0 plus 1. The second trapezoid is going to be the sum of the two bases, which is 1 plus 4. The third trapezoid will be 4 plus 9. And the last trapezoid will be 9 plus 16. So what I'm hoping that you can see is that this base, which is this one right here, gets counted twice. This base, which is right there, gets counted twice. This base, which is right there, gets counted twice. And that should make sense, because the first one here, where the 1 is, it's part of the first trapezoid, this one, and the second trapezoid, that one. So of course it gets counted twice because it's part of the trapezoid for 2 different trapezoids. And then the 4 gets counted as part of this trapezoid and that trapezoid. So the only 2 bases that aren't going to get counted twice are the very first and very last base. So we could do it the way we just did it. We can add all those up, and there's absolutely no problem with that. But a shortcut would be to do 1/2 the height, because the height should always be the same. I'll show you an example where they're not, but it's going to be much more clearly labeled. Times the first base, so base 1, plus the last base, whatever that happens to be, we'll call it b sub n, plus twice all of the interior bases, which is b2 plus b3 plus all the way up to the next to last base, which is b sub n minus 1. It just basically means the next to last one, because it's the one right before the nth base. So there's a shortcut to be able to do that. In any case, if you were to take the stuff that we already did and add it all up, you would actually get 22. Okay, so we know that our midpoint was 21 and this one was 22. Those two values are very close, and as you can kind of tell by the sketches, at least, they should be relatively close. It looks like 22 is definitely a slightly over approximation. 21 happens to be a slightly under approximation. You wouldn't necessarily know that by looking at the midpoint from the previous page right here. As it turns out, there is slightly more space underneath than there is above when you do that specific midpoint. But again, you wouldn't necessarily know that. So in the bottom question here, when it says which method would give the best approximation, in this case, we would say that either the midpoint or trapezoid should both be very close. And the reason is because the difference in the areas is at its least. So the difference in the areas are at the least. From the left and the right hand approximations, they were clearly, one was way over, one was way under. That was pretty clear. All right, let's go ahead and do 3 actual examples then. So it says a tank is being filled with water using a pump that is old and slows down as it runs. The table below gives a rate at which the pump pumps at 10-minute intervals. Typo there. If the tank is initially empty, approximate how much water is in the tank after 90 minutes. So what we have is we have a rate of so many gallons per minute, and we have an elapsed time in minutes. So it says the tank is being filled with water using an old pump. The table, and it slows down. What you should be able to see is the rate of change is slowing down as it goes from left to right as the time gets bigger. The table below gives the rate at which the pump pumps at 10-minute intervals. If the tank is initially empty, so we're starting off with nothing, approximate how much water is in the tank after 90 minutes. So the general idea is, if we want to figure out how much stuff we've accumulated, how much water has actually been pumped into this tank, we need to approximate it using our 4 different methods, and we have 4 of them. We have a left hand, a right hand, a midpoint, and a trapezoid. So I'm going to start off by doing the left hand. It doesn't really matter which one you start off with. Again, I call it the Lram, left Riemann approximation method. We haven't really talked about this thing called Riemann, but he's the person who invented it, this method. All right, so here's what we need to do. We need to think of this as a graph. You don't want to take the time to graph every single one of these points. That would be very tedious and very long. But if you were to graph all of these points, this right here, the elapsed time, is your independent variable. That's basically going to be like your x values. And the rate is going to be up along the y-axis, so that would be like your y. The difference between the x values is the base of the rectangle. So from 0 to 10, we've got a base of 10. These values are the heights of the rectangle. Well, if we're going to use a left approximation method, that means the upper left-hand part of the rectangle So if you think of this as being a rectangle, the upper left-hand part of the rectangle gives us the height of the rectangle. So the first height that we're going to use is 42. That's the upper left-hand part of the rectangle from 0 to 10. Plus. Now if I were to draw another rectangle that's sitting adjacent to the first one, now the upper left-hand part is going to be 40. Then 38 for the next rectangle, and so on. As a matter of fact, the only value that we won't use will be 10 because it has nothing to the right of it to make an upper left-hand part of the rectangle for. So we won't use the 10 in that case. So we're going to add all of these values. And notice that I have not multiplied any of them by 10 because 10 is the base for every single rectangle. So instead of multiplying every single thing by 10, let's just have the 10 on the outside. Obviously, you could distribute the 10 through and every single piece would get multiplied by 10. But instead, we're just going to do it like this. Now, this is not something I would expect you to be able to do. Well, you could do it without a calculator, but go ahead and use a calculator to do these approximations. If you add up everything in the parentheses and multiply it by 10, we would get 2,890, and we have accumulated an amount of gallons. So the units here are important. Okay, we've accumulated the amount of gallons of water in the tank. Okay, now let's do a right Riemann approximation method, or the right-hand method. The only difference here should be now we're using the right-hand part, so I'm going to erase these. We're using the right-hand part of the rectangle. So again, here's my rectangle. Now the upper right-hand part, now remember it's the y values we're looking at. The y values give us the height of the rectangle. The right-hand edge is going to be given by that piece. So that's the height of the first rectangle. Then I'll draw a rectangle to here. That's the height of the second rectangle, and so on. The only value that we won't use is that 42 out in the front because it has nothing to the left of it to make 42 the right-hand edge. So we just need to make sure that we add up all the different pieces, and we will actually use the last piece here because that last piece is the upper right-hand corner of a right Riemann sum. And then don't forget to multiply everything by 10 because that is your base. Okay, adding all those values up, I've already gone ahead and done all this, is 2,570 gallons. It's 257, then we multiply it by 10. Okay, midpoint method. Okay, a little bit more challenging here because the midpoint method, there's multiple ways you could go about doing this. I didn't specify in the problem here how many intervals I wanted you to use. So in our case, what we're going to do is we're going to say we're going to use the same amount of intervals. So 0 to 10, 10 to 20, 20 to 30. It might actually specify that you use less intervals or more intervals, in which case you'd have to figure that part out. For example, let's say that we wanted to use, well, actually, we can't do it in this case, so never mind that. I'll come back to that in a different point. But the problem here is, if we go from 0 to 10, the midpoint of 0 to 10 is at 5. I don't have a value in between here. So all we can do is average the two values and say that that's what our midpoint would approximately be. We don't know it for a fact, but we can average them and say it's going to be a good approximation. So you're still going to have 10 for your bases. Okay, the base still goes from 0 to 10, but the height is going to be dependent upon what we think it would be in between 0 and 10. So at 5, well, that would be the average of 40 and 42, which is 41. And then we're going to have to average all the rest of the pieces. So the average between 40 and 38 is 39. Between 38 and 35 is 36.5, I believe. Yeah, that sounds right. The average between 35 and 35 is just 35. 32 and 35 is going to be 33.5. 32 and 28, the average is 30. 28 and 20, the average is 24. 19 and 20 is 19.5. And 10 and 19 is going to be 14.5. I think that's right. Adding all that stuff up and then multiplying by 10 gives us 2730, I think, 2,730 gallons. You might want to double check my math on that one, but I'm pretty sure that's right. All right, and then the last part of this one was, okay, so those are three approximations. It's quite obvious that the red one is probably over because it's a large number. The blue one is probably under. It's much smaller. The one in the middle, the 2730, is probably a much better approximation of this midpoint, but we still have one more to go, which is our trapezoids. And our trapezoid approximation, remember the idea was it's 1/2 the sum of the bases times the height. So the 1/2 is always 1/2. The heights here are all going to be the differences here in the x values. So the heights are always 10. And the bases are the y values because they're always parallel to each other. So remember what I said, all of these interior bases get added twice. Only the last and the first base get added once. So we can use that idea to simplify this just a little bit. So let's see if I can fit all this on the same thing here. So it looks like 42, oops, it moved, plus 10, because that's the first and the last, plus twice all of the other bases. 40, 38, 35, 35 again, 32, 28, 20, and 19. Just makes it a little bit easier, a little less work than doing every single individual trapezoid. That would take a long time in a case like this. All right, so when you add all this stuff up, I believe that we also get 2,730 gallons. Okay, and believe it or not, that is not coincidental. That works out for a reason in this particular case. All right, I could continue this and do the last two problems, probably make this a really long video. Instead, I'm going to come back and we are going to do the last two problems in one video. Should be about 10 minutes max in that video.